Yeah, it's flashing. Okay. Okay, so thank you for inviting me to give this talk on the work we have been doing on the sum rules of the electromagnetic response functions in 12 carbon. I mean, the collaboration is pretty wide for my standards, and I mean, it involves people from Los Alamos National Laboratory, Argonne, University of Tennessee, and Jefferson Lab. Okay, so the we have computed the electromagnetic response sum rules of the response functions, but this is a first step toward the calculation of the electroweak response, which is a fundamental ingredient to describe neutrino 12 carbon 12 scattering that has been recently measured by the Mini-Boom collaboration at Fermilab to calibrate the detector, which is aimed to study neutrino oscillation. I mean, this is a picture of the. Here we are. This is a picture of the inside of the Mini-Boom detector. These are Cherenkov detectors, and I mean, they measured at relatively low energy. The measured cross-section is above the theoretical, is larger than the theoretical calculation. However, I mean, our calculations are important on their own because these are we want to predict the results of the Jefferson Lab experiment. And they are doing inclusive electron carbon 12 scattering. So they are really computing the electromagnetic response. So we are actually interested in this process where an electron scatters off a carbon, then another electron comes out, and whatever. I mean, the carbon can be disintegrated by scattering. Okay, so the important point is that this cross-section is inclusive, so we don't measure the final state X is not measured. And in that case, the cross-section can be written in this way. As you can see, alpha is the.
What energies? You didn't specify the energies you're going to split.
Well, I mean, I'll show you a slide in the next slide anyway. I mean, the momentum we are considering is up to 800 MeV, and the.
Transfer momentum?
Yes, transfer momentum, yeah. Anyway, okay, so in this as you can see, the Feynman diagrams can be factorized in two parts. The first one is the leptonic one that can be treated in perturbation theory, I mean QED. One of the beautiful aspects of QED is that everything can be computed in perturbation theory in terms of the fine structure constant. And the leptonic tensor is fully specified by the kinematic variables, I mean, the incoming and the outcoming form momentum of the electron. While, I mean, all the hadronic physics is contained in the hadronic tensor, which has these structures. Basically, the currents, the four currents, operates the transition between the ground state and the final state X. And there is also a form momentum conservation, delta function. So this is a schematic representation of the inclusive cross-section. So this is for momentum transfer at around 400 MeV. At very low energy transfer, there are excitation of the nucleus. Then, as the energy increases, we found the quasi-elastic peak, and this is mainly due to the fact that the electron can scatter on individual nucleons, but these nucleons are correlated in the nucleus, so that this is not a delta function. Otherwise, the scattering on a free nucleon will give a delta function. And then other degrees of freedom are excited. And in the very end, we have the deep and elastic scattering, and we can see the actual constituents of the nucleons. Why this is, for example, some information can be derived from the shape of the peak. One of these is, for example, the average momentum, the momentum distribution of the nucleons inside the nucleus. So at moderate momentum transfer, say, the very maximum would be like 800 MeV, but in principle, non-relativistic wave functions can be used to describe the initial and the final state, and the currents operator are expanded in power of momentum transfer over the mass of the nucleon. In this case, in this approximation, the hadronic tensor can be written in terms of the longitudinal and transverse response function with respect to the direction of the 3 momentum transfer. So once the direction of the 3 momentum transfer is chosen, we have a longitudinal response to the system to this longitudinal excitation and a transverse response to the excitation. So in the longitudinal response, the transition operator is the density, while in the transverse is the current.
So that's, there are 2 vectors in that equation.
Yeah,
so you mean that to take the same transverse component in each j sub t?
Yeah, there is like a scalar product here.
Or it's a scalar product?
Yeah, it's like jx plus jy, jy.
Okay.
And, yeah.
No,
In principle, you can.
okay. You mentioned that you're going to use no relativistic wave function, but energy transfer, the quasi-elastic peak, it's about 2 to 400 MeV. So that's about half the energy of a mass and rest energy of a nucleon. So it's quite high, and mostly it's transferred to one nucleon at that point. So that nucleon is going to be relativistic, you see, no question about that. So you see that first statement, I think it looks a little bit dubious to me.
Well, the point is that in the currents, there are relativistic corrections. And we are not actually computing the transition, as I will show you in the next slide, that we are not computing actually.
If I go back, you see, to the diagram, you see that most of the cross-section is in the quasi-elastic peak.
Sure,
right?
but
And there, you see that the energy transfer is 2 to 400 MeV, so it's a lot.
no. In fact, yeah, but the point is that we are not
The final state of the nucleon is relativistic.
Okay, so
He's going
In-
to avoid that problem.
Well, you see,
I-
in the statement at the beginning, you see everything else, you didn't discuss it, and I think you see that's
So there's one
important.
fast nucleon and the rest are slow.
What he's going to do is
Well,
sum
the-
rule
I'm sorry.
and
No,
avoid using the excited states.
no, okay. Can I? Okay. The point is that when the momentum transfer is high, you can do the impulse approximation, so that actually here you can factorize the only nucleon scattered. So you have like a transition between a nucleon here and a relativistic nucleon there, a single one. But you have to compute the spectral function for the superposition of the remaining A minus 1 state with the A state. I mean, with the superposition with I minus 1 and I minus 1 state. And this is where nuclear physics enter. Okay, so the excited states minus, if you want, the scattered, the single nucleus. But this is not what we're going to do now, because
I
we're.
understand what you're saying, but honestly, I'm not convinced it's correct, but anyway.
No, I mean, but anyway, I'm not doing that. I'm computing.
An answer, so please go on.
Okay. Anyway, I mean, the direct calculation of the response requires the knowledge of the excited states and of all the transition amplitudes. On the other hand, we are not computing the response, but we are computing the sum rules. So if you integrate over the energy transfer, you can use the completeness of the excited states here to derive an expression that only depends on the momentum transfer. So I mean, it gives you less information than the actual response, but can be easier. It can be computed easily. I mean, fairly easily, because it involves only expectation value of operators on the ground state. So we do not have to worry about the actual transition. So we don't have to worry about the final state.
Well, you see, with this I don't agree. Because when you sum over all the states, in order to get the sum rule, you have the density of states. The density of states of non-relativistic system is different from the density of states of relativistic system. So I don't agree, you see, that you are going to avoid the problem, as you said.
No.
Well, but the point is that
Depends on what the operator
if the operator allows for
You
transition,
sum for over parts of energy which are high, relativistic, and there you have a density of states which is relativistic.
Yeah, but he's integrating a
Yeah.
delta function. He integrates delta of omega minus h
Yeah.
on omega. So it's not one.
I mean, the point. I mean, but you're right. I mean, if the operator is, if the
But the integrand is different.
I mean, no, the point is that if the operator allows you for, I mean, as the correct one to numbers, and I mean, and if the operator allows you to go to this state, then it's okay. If not, and in our case, in fact, it is not completely true, this is not correct. I mean, this is not correct up to 2 GeV, of course. But I mean, 800 MeV, it will be like the limit. 600 MeV, I mean, like that order of magnitude.
Yeah, there have been reactions by Keister and Kastek, and also by Colton. So the issue of relativistic stuff is a thorny one. Maybe best discussed after you tell us what you did.
Okay. So anyway, I mean, so let's move forward. I mean, the longitudinal sum rule then is defined this way, where the elastic contribution is removed. So you see here the carbon is cut. I mean, the final state is again the carbon, and we want to remove this contribution, and this contribution is proportional to the longitudinal form factor that we also computed. On the other hand, this is the transverse. The transverse sum rule is defined this way, and these coefficients here are introduced in such a way that in the limit for q that goes to infinity,
I think you need a G squared.
Yeah, here there is. Here, here there is a square. I forgot it here. Yeah, thanks. Yeah, that's true. Even also here. Yeah. Anyway, yes, you're right. In this way, with this normalization, the sum rule goes to 1 in the approximation where charge and currents operator originates only from the magnetization of the charge and spin magnetization of single particles, and the relativistic corrections are ignored. So I mean, it's like the physical limit. Okay. However, I mean, computing in order to compute to compare the sum rules with data is not straightforward. I mean, it is not direct. So the sum rules have to be extracted by data. And the point is that in order to determine experimentally the sum rules, one should measure the response in the whole energy transfer region and then integrate. However, I mean, the inclusive electron scattering experiments allow you only to to investigate in regions where omega is less than q. So then you have to, these are the experimental value, and then you have to extrapolate the tail. Okay, usually the tail is, at least what we did, we extrapolated the tail with normalized deuteron-like response. Because we think that when the energy transfer is very high, I mean, really only the pair correlations are the prominent ones. So again, in principle, one should integrate, if one had experimental data all over the omega transfer region, one could just integrate the response. But since the experimental data arrive up to a certain omega max, then one needs to extrapolate out. Because these are in one curve the cutoff is, one is normalized and one not, depending on the form factor. So we want to do ab-initio few-nucleon calculation. I mean, ab-initio, we're not doing QCD, unfortunately, I would say, but I mean, in the sense that we are not able to do this now. Nobody is doing QCD for this system as large as this one. We are using a high-precision phenomenological potential, namely the Ergon V18 potential. As you can see, is a sum over 18 spin and isospin operators times a radial function. And the shape of the radial function is determined by fitting of the 4,300 scattering data of the Nijmegen database. And the operators, I mean, the first 6 operators, as you can see, they act on both the spin degrees of freedom and the isospin degrees of freedom. These are the spin of particle iaj, the scalar product of the spin matrix on particles iaj. This is the tensor operator. Then there is the spin orbit, which is necessary to reproduce the p-wave phase shifts. And then, I mean, the remaining operators are more complicated. They include also charge symmetry breaking, and they're needed in order to explain to reproduce the scattering data with the chi-square, which is of the order of 1. Well, I mean, a key point is that we are consistent in the sense the currents have been derived consistently with this potential. So the currents are conserved. The current is conserved. In order to compute the sum rules and the form factor, the ground state wave function of carbon-12 should need to be known precisely, because remember, the sum rules are expectation value on the ground state of the product of 2 operators. So an accurate 3-body potential has to be introduced. We are using, I mean, in the standard picture, the Urbanan in our framework, the first three-body potential that had been derived was the Urbana potential, which contains the Fujita-Miyazawa term with a delta excitation in an intermediate state, plus a phenomenological repulsive term, which is needed to explain saturation density of nuclear matter. More recently, the 2-pion S-wave contribution has been included along with the 3-pion rings. Like in the two-body sector, the 3-body potential is a sum again of this contribution, and each of these terms is an operator in the spin isospin space. So this is the final result of GFMC that now I'm going to introduce. As for the energy, as you can see, the spectra for the ground state and the low-lying exciting states of light nuclei is very well reproduced by this Hamiltonian. In particular, as you can see here, from the carbon-12 to the, from the helium-4 to the carbon-12. So this is really, and the Illinois force has been introduced mainly to explain the energy splitting of the excited states.
So what changes in that diagram every 6 months or so, or every year? Because you see, I've seen the diagram all the time, and I don't know the changes.
Well, this one.
Maybe you know.
Bob.
Things are very gradually being added at the end, but Steve always insists on putting a date on it. I always ask him for give me a figure without a date.
So the light nuclei didn't change, it's only
The light nuclei have not changed for quite a while.
Yeah, so it's only carbon-12 and
Carbon-12, in fact, he could also have been putting up a 2+ date.
Yeah.
So
Yeah.
the rest is old calculation.
Most of it is old calculation.
I arrived in Argonne just at the beginning of that month, so I take this one as my my reference picture. So, okay, so now I'm going to explain a little bit of Green's function Monte Carlo. So, as you know much better than me, solving the many-body Schrödinger equation is, an incredibly difficult task. And moreover, in this case, everything is made more complicated because the interaction is strongly spin and isospin dependent. So imagine if the wave function can be expressed as a sum over the spin and isospin state of the many body nucleus of the nucleus of interest. And as you can see, the number from this plot, which is in logarithmic scale, the number of spin and isospin state grows exponentially with the number of particles. There is actually exponentially with the spin states grows exponentially, and the charge state grows exponentially, but it's less dramatic just because of charge conservation. So if we want to solve really the Schrödinger equation for carbon-12, we would like to we should solve more than 260,000 second-order Kaplan differential equations in 36 variables, because there are 3. Because of the center of mass. Yeah. Okay. Yes. Still. Yeah. Yeah. No. It's in fact this number.
No question about it.
This number is not even that. It's twice as that. But the last one, the isospin of the last particle is determined by CPT. Yeah. By the time yes, time reversal symmetry. Okay, so the Green function Monte Carlo, as you can see from the name, uses projection technique to enhance the ground state component from a starting wave function. But the trial wave function is very complicated because, I separate every contribution of this wave function. So to start with, there are 3-body correlations originating from the 3-body force. So, these are operators. And moreover, this pair-correlated wave function is written in terms of the operator correlations. So this, again, is a symmetrized product to take into account the fact that operators do not commute of spin and isospin operators that have the same shape as those appearing in the potential times a Jastrow wave function. And the Jastrow wave functions contain scalar 3 and 2-body correlations times the anti-symmetric wave function, which really depends on the nuclear state. In the case of helium-4, everything is in the S, and everything is in the S shell, so everything is easy.
This is all good isospin?
Well, yeah, we use usually, good isospin to reduce the computational complexity. So actually, the number of states is less than. But in order to do the calculation, since the currents do not preserve the isospin, we have to expand in the charge basis. So this is how the wave function looks like. It's a complex vector of this size, and only the, it depends on the size of the font, but choosing a reasonable size, only the tritium fits in the slide. And as you can see here, this is like you have an amplitude for each of this, considering only the spin, I have a complex amplitude for each of the possible spin configuration. And when I apply an operator like sigma 1, 2, for example, I change the spin and the spin amplitude for each configuration. So each imaginary time step consists in a 3-dimensional integral evaluated within the Monte Carlo approach. But moreover, the gain function is actually a matrix in the spin and isospin state. And the short time propagator is constructed. Okay, so the short time propagator is constructed from the exact two-body propagator because we can solve the two-body Schrödinger equation. And what is the key advantage of this approach is that, usually I like the term totalization. So in the totalization usually in the standard one usually makes an error of the order Vij, kinetic operator Vij, delta cube to the cube. However, if we really solve the two-body propagator, and this error is large when two particles are close to it, very close, because otherwise Vij tends to 0. Otherwise, solving the two-body Schrödinger equation and using the short-time propagator allows you to make an error which is of the order Vij t Vik, and this is large only when two particles are close to each other, which is less probable. We have to face with the sign problem, and not going in the real detail of this, also because I'm still learning. And however, the point is that we do not only sample the particle coordinates, but also the ordering of these correlation operators in the trial wave function. So we cannot use the standard constrained path of fixed node algorithm, but we have to slightly modify it. However, to control the sign problem, one can relax at a certain point the constraint and see what happens to the energy. Okay, usually the error grows, but then if the trial wave function is accurate enough, what happens is that the energy stabilizes for a while, for some steps, so for some unconstrained steps, and you can really understand what the energy is. This plot shows the relaxation of the constraint for two different starting wave function, nuclear wave functions for the carbon-12. As you can see here, at the beginning, the energy are not fairly different, but then, they are compatible within statistical error, but still, the richer wave function gives a lower energy with respect to the other one. Now, since I'm employed by the computing department of Argonne, I have to advertise it. I had to advertise what I did, and it's also, I enjoy doing this. So, okay, so forgive me about these technical details. Anyway, a fundamental process in the green function Monte Carlo algorithm is the branching. And usually what one does is, okay, I take some worker and I distribute a certain amount of them to each rank. And then I let them evolve. So, in the original version of the code, where the computer was not as huge as the one I'm using, like a reasonable number of workers was on each rank. So even if you have fluctuations, you never reach 0, or you never reach you never reach actually 0 worker on each rank. And the algorithm is efficient. However, a typical carbon-12 calculation involves around 15,000 Monte Carlo samples, and leadership class computers like Mira have many, like order 13,000 processors, even more. So the algorithm will be very inefficient because we have ranks without walkers, or ranks with just one walker, and then if it dies, it dies. You have to wait to re-equilibrate. So how do we solve this? We implement ADLB library. So in this way, the nodes are organized in servers and slaves. So the first thing to say is that usually 3% of the nodes are servers, and they do not compute anything. I mean, they do not. I mean, they do think that they compute, but they do not compute anything related with the Monte Carlo algorithm. They just manage this queue. Okay, so there is a shared work queue, which is managed by the servers, that is accessed by the slaves. And the slaves can either put some work in the queue, some work to do, or can take, and this is the node that does work package, or it can get some package and work on it. So it's not anymore synchronous, but it can be asynchronous. So they can put and they can take. And the servers manage the queue in such a way that there is always some work to do, and there is space to put the work package. However, I mean, then once the work is done by one slave, the result is put again in the pool, and the servers do their job in such a way that the slave which originally put the work package in the pool actually take the answer. But the work package could have been processed by another slave. Okay, so nobody is really resting, like the postdocs. So the implementation of the ADLB library in this case is, I mean, in order, now I will explain how the ADLB has been implemented for the response. So in order to reduce the statistical error associated with the calculation of the response, the sum rules are evaluated for 12 directions of the momentum transfer that are organized in 4 groups of 3 orthogonal directions. And the grid of the magnitude of momentum transfer has 21 values. So in total, the response has to be the sum rules have to be evaluated for 252 values of momentum. And values of momentum, I mean the direction and a value of the magnitude. So the evaluation of the sum rule for the carbon-12 for a single value of momentum transfer takes about 360 seconds with the 16 OpenMP threads. And ADLB is split in such a way that each slave computes the sum rule for one single value of momentum transfer.
Is this per step?
Yeah, per configuration. For a single configuration, for a single value of Q, okay, it takes 360 seconds on 16 OpenMP threads. Yeah, so I mean, just I don't want you to enter into the code, but anyway, since the derivatives of the wave function enter in the calculation, this package is huge, and it can be as big as 1.3 gigabytes. So you have to imagine a lot of work package going around, and each one is as big as 1.3 gigabytes. And this was impossible in the previous machine, so we really need Mira. This is the performance of the ADLB library as for the energy calculation. As you can see, you can go all the way up from 1,000 ranks, MPI ranks, to more than 2600,000 ranks with spectacular efficiency. And this is only possible with the ADLB, because otherwise, without ADLB, you should have a number of configurations comparable with the number of ranks. I mean, actually 10 times the number of ranks, and it's useless. And this is the scaling for the calculation of the response. I mean, I didn't go all the way up to, I mean, I didn't need in the end, but still I used more than 32,000 ranks. And as you can see here, the total wall time per configuration, per Q value remains stable, very close to the ideal case. Okay, I have to, okay, yes. So these are the results. These are, actually, it's not the sum rule. This is the longitudinal form factor. So it's the 0, I mean the 0, rho, and then you have the final state with a certain momentum, proportional, I mean, proportional to this matrix element. And as you can see here, the experimental data are the blue squares. When you include only the one body term in the density operator, you get the open circles, but when the two-body terms in the current are included, as you can see, the only difference is in the tail of the high momentum transfer, and they bring the calculation in closer agreement with data. And from the Fourier transform of this quantity, you can get the charge distribution inside the nucleus. And as you can see, again, the calculations are in very good agreement with I would say very good agreement with experimental data. And again, it is important to remark that the two-body contributions really bring in the high momentum tail, in the high momentum tail, the results in closer agreement with experimental data. Okay, these are the results for the longitudinal sum rule. As predicted by, as you can do the calculation analytically for small momentum transfer, the sum rule vanishes quadratically. This is the case. And as you can see, in principle, if you do not consider relativistic corrections and convection term in the limit of infinite Q, it is not a physical limit. It's just you take the, because otherwise you have to, you're neglecting relativistic correction, convection term, and you take just the limit. You have to go to, it should tend to 1, but it does not because of these corrections. However, these are the data without, okay. So the red line is the open squares are the experimental data without tail corrections. So you just integrate up to the maximum omega given by experimentalists. And the blue squares take into account the tail correction. So we extrapolate the response to larger omega and we integrate say it again?
Why does it go down? Integrating a positive number on omega.
Yeah, in fact, it goes up from here to there.
Oh, it's the white.
I'm sorry. Yeah, maybe.
Square is in the white.
Yes. I'm sorry. Maybe I said the other way around. Okay. No, this is without tail correction, and this is with tail correction. The red line is the one obtained considering both one and two-body operators in the current, two-body terms in the current, while this one, the dashed line is considering only the one-body term. As you can see, the two-body terms here have some effect, but it is not dramatic. The agreement with the experimenter is satisfactory, but maybe, but we are waiting for JLab data. And there are no evidence for significant immediate modification of the nucleon electromagnetic form factors. There is room for some modification, but it cannot be dramatic. Now, these are the results for the transverse sum rule. Okay, this is more complicated. Anyway, again, let's start from the experimental data. Open squares are refers to the response integrated up to the maximum energy transfer allowed by experiment. Once the tail corrections are added, we get the blue squares. And our calculations, the one-body results is this one. The two-body results are these two curves. And as you can see here, the enhancement is pretty large, as expected. However, and this in particular, the full line is the full result with the derivatives taken into account, because in these current operators there are derivatives, and ignoring the derivatives we get the dashed line. So the divergent behavior as small q is due to the normalization form factor that goes like 1 over q squared. However, here the comparison with experimental data is more difficult, because our currents operator do not account for the creation of delta. Okay, so we cannot. In the plot that I showed you at the beginning of the response, there was the quasi-elastic peak, and then there is the delta peak. Our operators do not allow for the delta production. So we are not including the strength of the delta peak in this sum rule. However, there is a large two-body contribution from the quasi-elastic region, which is needed to agree for a better agreement with experimental data. And this is, fairly well-known feature for the transverse response. So let me go to the first part of the conclusion. Okay, so we have a very good description of the longitudinal form factor, and the two-body term bring theory in closer agreement with the experiment, although their effect is really appears only at very large momentum transfer. As for the longitudinal sum rule, the agreement with the experimental data is satisfactory once tail corrections are included. And we don't find evidence for a strong modification of the nuclear electromagnetic form factor. In the transverse sum rule, we observe that the large two-body, a large contribution arises from the two-body terms, and this is really necessary to explain experimental data. So these are the physics conclusion, and now for the computing science, we got a very good ADLB scaling, and it was really, a great effort to achieve this, up to more than 32,000 ranks. At least, I could go beyond, and I think I have to go beyond for what I will tell you in the next slide, using 4 ranks per node. Moreover, there is a good OpenMP scaling, and we used 16 threads. So we used 4 ranks per node, and 16 threads is the maximum allowed by the node of Mira, by the machine. Okay, and using 16 threads instead of 4 reduces the computational time for configuration from 12 minutes to 6 minutes, these 360 seconds I was mentioning earlier.
Alessandro?
Yes.
So you said that it doesn't, the current operators that you have don't account for the deltas.
Yes.
Doesn't that mean that your theory should always be below the experiment?
Yeah.
There was at least one point where it was not.
Yeah. Yes. Yes. But
you have a sign there. You see that they have to interfere with those contributions. Could be
Pretty
distracting.
much a positive here?
What?
Pretty much orthogonal final state.
So then they add up.
Yeah, pretty much.
Yeah, it's not.
No, but that's an intermediate state. You see. Yeah, probably they add up.
Yeah, in the end, you don't really see the delta.
No, I got your point.
Okay. So, okay, what we want to compute now, the neutral current sum rules, so including really the electroweak transitions, which will allow us for a description of neutrino scattering on carbon-12, and they are currently implemented in the being implemented in the code. And we also want to compute the Euclidean electromagnetic response that will enable us really to make a more direct comparison with data, because using, as we learned from the talk of Alessandro, but you already knew before, inverting this, there are techniques allowing one to extract the response from the Euclidean sum rule. We have to invert this kernel, which is very difficult, but in principle is doable. And in particular, the evaluation of this operator in Monte Carlo corresponds to, the calculation of this expectation value. As you can see, we have to start from the ground state to apply the operator. It can be the current, the density, evolve it in imaginary time, and compute the bracket with the bra to which the operator is applied, the transition operator is applied. So usually when one says, the future now, I did some calculation while I was here for the neutral current sum rule. This is helium-4, so much smaller than carbon-12. And here I'm not dividing, this is the transverse current. I'm not dividing for the form factor, okay? So this is why the curves look very different from the other one I showed you before. I had no time to divide it for it, I'm sorry. But what I wanted to point out is that, again, the two-body contribution is large. Okay, so it's really, I don't know now where experimental data are. I don't have the...
Where's the one body?
I'm sorry. Yeah, the one body is here. Yeah, because I made this mistake. I went to a web. This is a nice. Now this is a nice explanation. The actual explanation is that there are these now we discovered this website where there are these color combinations that in principle are very nice for the eyes, but maybe I chose the. Maybe they are not so nice. At least not so as visible as nice. Okay, yeah, this is.
So do you calculate these do you use forward walking for this, or use something like repetition? How do you calculate
I'm sorry, say it again?
What are you using to calculate? Are you using
Ah, no, okay, this is actually variational Monte Carlo calculation. Okay, but in general, for green function Monte Carlo, I do the mixed, I mean, the usual way, the mixed expectation value, and then I perturbatively correct with the wave function.
So on one side, you have the trial wave function, you're saying?
Yes. Which is, I mean, for the energy is not, I mean, for the energy is good, is not great, but for these operators is much better. I mean, really the green function Monte Carlo correction to the variational results are not as dramatic as for the energy. Because for the energy you have a large compensation between the kinetic part and even in the two-body sector, we have a large cancellation between the kinetic part and the potential part, because the potential is really very repulsive. So the wave function is really, I mean, if the potential is there, the wave function goes down, and then you have a large derivative, and then you really have to compensate this. This is why the SRG, I mean, these techniques of smoothing the potential that lowers both the kinetic energy and the potential energy, keeping the value of the energy fixed work. I mean, this is the idea behind that. I mean, because they want to avoid the hardcore. So, yeah. So this is the end, the future, but it's the end for now. I mean.
I have a quick question. Is it totally out of reach, the calculation of some energy weighted sum rules?
Well, then you have commutators with the Hamiltonian and the operators. I mean, if we compute the Euclidean with...
I said, get to work.
Well, but I mean, if you compute the Euclidean, then it can be another constraint. Do you think it's useful when you want to invert the Euclidean response, yes, having also some weight?
That gives you at least some vague idea of what you should get out. I mean, it's a sort of consistency check at that point, which could be useful if I mean, if you're totally blind,
yeah,
essentially, you have experiments, but I mean, if you really want to see the sort of some kind of internal consistency, that's a good way of checking it.
So using both the, I mean, yeah.
Experimentally, the thing might not converge because you would emphasize the tail, high omega tail.
Excuse me?
If you do that with an extra h with 2 powers of h, you get omega and omega squared, you emphasize the tail.
Yeah.
So for theory purposes, it might be good.
Yes.
Could cause trouble for the experiment. So what GE did you use?
Hodler and Adler. The form factors, you mean?
Yeah.
Okay, we tried both with the dipole, and then Hodler and Adler, something. Yeah, another parameterization of the form.
Very old. You should use some updated parameterization.
Yeah, but Ingo Sik told us. Yeah, no, but Ingo maybe Ingo Sik told us. Okay, these are. I mean, we trust. We tried also to use the dipole, but as for I mean, here nothing changes. I mean, in the low momentum transfer, here there are some differences indeed.
Well, you divide by GE squared, so a small change, a 5% difference is a 10% difference.
Well, but I also have this. I mean, in some rules, I have in the operator, and then I divide. So, in the form factor, this is what would really. I mean, in other words, my results would not change that much. It could change. What really would change are the experimental points, because I mean, you divided the experimental points by the form. If you change the form factors with which you normalize the experimental points, they change.
Yes, that's what I'm worried about.
Yeah.
That you don't know what's in the numerator.
Yeah.
So you really should use the latest ones, and they're available to you. Barrington is the Oregon. That's the best fit. John.
Yeah.
How far in the,
Dipole form factor is
Definitely wrong.
up to
Oh, pretty low.
I mean, if you know
how far in the Euclidean response, how far in imaginary time can you go before the sign problem?
Yeah, I mean now with Steve we are like trying to make the time steps larger, for actual green function Monte Carlo calculation, and they converge pretty well, like making. So.
But you have a sign problem.
Yes.
12 and 12.
Yeah. No, I do have.
Probably not so much in the alpha part.
Then
but-
with
Yeah.
with our time step, you have to be careful what to find in the tails.
Yeah. No. Yes, but for the first.
Screwing up everything.
No. Sure, but. Yeah.
At some point you have shown that you can calculate the Green's function and approximate it as a product of two particle Green's functions.
Mm-hmm.
How do you get the two particle Green's function?
You really solve I mean, you have to solve the Schrödinger equation for each partial wave, because in our case we really, Bob, correct me if I'm wrong, but in our case we really have a strong spin and isospin dependence, so you have to put really.
But then do you calculate on the fly during the simulation?
No. We store them. We compute it at the very beginning and then we store them. Yeah. So there is a different green function for different times. We have a table for each time step that we want to use.
It's a multidimensional matrix, I guess.
Sorry?
It's a multidimensional
Yeah.
matrix, baby.
Because of the spin and isospin degrees of freedom. Yeah. So it will be better to compute everything at the very beginning and store it, because otherwise.
There's one thing more that should be said. Oro was asking about relativistic corrections, and people tried to see if there was a relativistic version of the sum rule. Sum rule derived non-relativistically equivalent forces. That people put in the Dirac equation and things like that. It got rather complicated. So you might, if you're going to proceed to compare to the JLab data, which is coming out, it's being analyzed now from Messiani, you may want to look at papers by Colton,
Mm-hmm.
who wrote papers on the sum rule, and there's a long literature with Oleska and people like that, putting in the Dirac equation instead, and it's not even clear to me that there is a sum rule. So there are a lot of open questions related to that, so if you're going to work on this, you might be aware of it.
Okay, thanks.
So it's hard to use completeness once you have the Dirac equation?
Yeah, I mean, negative energy
Because of the
states.
negative energy
Yeah,
states, okay.
yeah, I've never really understood those papers yet.
No, it's clear to me.
So it's quite, it's a little bit hazy what the experimentalists actually measure.
But by not being a sum rule, you mean the energy integral is not equal to ground state
Right.
expectation.
You see, once you have negative energy states, you see the completeness includes
Yeah,
both.
sure.
Yeah.
And in this type of treatment, you include only part of the spectrum, you see the real
Yeah.
spectrum. I
So
think
there's
this
a
is the
long
point.
literature, there's at least 5 papers on it.
Well, because you should really, you should really put in real pions, not only virtual, right?
Right.
Yeah, so, the optical theorem is still there. I mean,
Get to work.
yeah, but the point is, yeah.
Before you flock away, in the afternoon at 2:45, here in this room, Markellos will tell us an interesting story of an intractable problem that becomes tractable if you manage with it in
You have to be more specific.
he can be more specific. You can be more specific.
No, because,
What an abstract.
Yeah.
yeah,
What's the
intractable
title?
problem, what's the result? Things like
It's
that.
not quantum Monte Carlo.
Well,
So if
that's
if
it's
your
about the
interest
stock
is
market
only in
then.
quantum Monte Carlo, stay away. It's about particle transport and branching processes.
Mm.
And a branching process that diverges, and how to solve it, how to treat it in Monte Carlo in a finite time.
So this is what you mentioned, the reactor problem.
Right. Or actually, the closest, it's important especially for safety of stored fuel. You want to be sure that you store it in a configuration
You mean nuclear fuel?
which doesn't multiply. And that's the precise question. But as a Monte Carlo problem, it is.
These are more fewer nuclear.
Is that a good enough abstract?
Yeah. It gave us an idea.
Pardon?
It gave us an idea about what's going to
Right.
be, right?
I will also review what I call the classical theory of importance sampling, which.
You mean
You want
with the
to
critical
quantify.
eye?
Pardon me?
With the critical eye?
With a critical eye?
Yeah, but you review, but you're going to tell us old things, or you're going to do something new there?
Sorry.
New results or old results? He's asking.
Yeah, kind of. Yeah.
There's nothing new about the basic theory.
Okay.
You
On
should
the other
simply come
hand.
and find out.
All right. Choices.
The final outcome is a Monte Carlo calculation which converges exponentially fast.
I see.
So one of the interesting results is that there are Monte Carlo calculations that converge exponentially fast
Okay.
in computer time.
Okay, that's interesting. Thank you.
Schiaccia questo.
Take a.
I don't have to give the talk. Now, what did you say?